So now comes the key notion, which is, we already did it, but you didn't appreciate it because I discussed group orbits, but they look very boring. They were like 3 points or something in some state space. They didn't look very impressive. But the group orbit is now a much more impressive notion when you have a continuous symmetry. The group orbit of point x is a set of all points. I'll label it by point x. This is a set of all points you obtain from point x by applying group action to it, so actively moving someplace, for all group actions in a group. But when you have a continuous symmetry, there is a line of these in every direction, every parameter. The group orbit looks something like that. I have a point, here is a point x, and the group orbit says in this direction I can move my point, but if I have another continuous parameter, I can move it this way, and I can move it in any combinations of two parameters, and then, group abelian, non-abelian, etc. But it means that associated with any point, there is a manifold which we'll call mx of dimension n, where n is number of independent parameters. For example, angles. You can think of 3 Euler angles for rotation. Then it will be 3-dimensional group orbit, but there I cannot draw. So group orbit is a surface. And significance of this surface is that if I take my object and put it any place on the group orbit, it's the same object. So physics doesn't change under symmetry. So that means my world, my big state space, is now foliated into sheets. Each one of them has equivalent physical states on it. They're only related by coordinate transformation. There is no deformation done. So, if I have a turbulent patch in a pipe flow, I can change my coordinates and move it so it'll be someplace else, but it's the same patch that burns same amount of energy. It has all the same physical properties. So the symmetry for continuous symmetries foliates space into group orbits.